Today we had so many lectures about invariant solutions, and I'm not going to repeat what was already discussed, but just few words. First of all, about the groups, it's just everybody has his own notation. So I'm using my own notation, which is close to classical notation of state. Terminology is of course different, but still in some way close. Anyhow, we are dealing in group analysis always with so-called local groups, not groups. Local group means the group property is satisfied in a sufficiently small vicinity of the identity transformation. But the sufficiency means that smallness of the vicinity depends on how many multiplications of group multiplications we do. Sometimes, nowadays they call it pseudogroups and so on, but again it has names and so on, nothing else. Local group is not a group, but when you deal with differential equations, you always obtain these local groups. So group property is satisfied if the parameters of multiplication are group and parameters are sufficiently small. And this is due to the fact that when you solve differential equations, you always have solutions locally, not global solution. And here comes the name of the local group. Just because local solutions of the equations. Well, and all this notation you know, I will not repeat it. And this is the symmetry of the group, again, determining equation. And I try to make the notation as simple as possible for using. This is the main aim. Not for mathematical rigorousness, but for simplicity. Because I'm trying to make the calculations easy to make for applications not only in teaching, but also applications for engineers or engineering students. Well, now about invariant solutions. It was already explained many times. So, the idea of invariant solutions, let me try to explain the idea of invariant solutions. And I will use for that this whiteboard. We start with ordinary differential equations. You have one or a system of ordinary differential equations. Then the solutions of differential equations are curves in the space of dependent and independent variables. Simplest one is when you have one ordinary differential equation, first or higher order. So the solutions are, if you take so here x and y and x. X is independent here, y is dependent. So any curve, any solution is a curve in this space. Now, if you consider all solutions of this equation, it doesn't matter how you can calculate it or not. Just imagine all solutions. They fill a lot of solutions, big set. So let me just denote this set of solutions like that. Just for it's of course not. It's just a set of all solutions. Now, so many of them, and the equation is describing certain natural phenomena. Now, here you have, if you take it away, x and y. So, and say the equation is y prime equals f of x and y. So you have many, many curves here. And what happens? In the beginning, it was that you formulated differential equation not just in order to make some mathematical work, but in order to solve a certain concrete problem. In concrete problem, there can be different conditions. For example, you are interested in the easiest one if you are interested in a solution, which is a curve, which goes through a given point, x0, and say y is 0. So you take there, here, oh, then it doesn't count, then you have another one here. You need a solution which is going through this point. So you add to your equation initial conditions y and x equals to x 0 equals y 0. By this you single out one solution. So how you can solve this problem? This is initial value problem because it is called initial point where you start. Initial point is x over 0, y 0. So the curve starts from here. The easiest way, the best way, or the best way would be if you can write the solution of this equation, all solutions. All solutions are given by a function containing a function of x but containing arbitrary parameter. So you require this condition and obtain the value of that parameter, and you obtain a particular solution. And you don't care what are the solutions. But very often you don't know the general solution of the equation. General solution is a solution containing one arbitrary constant, arbitrary parameter. Then there are also possibilities, some kind of approximations. One of the approximations is can be obtained by numerical methods. Numerical method always gives a particular solution, and in order to find the solution, you need the begin. You should start the process somewhere. So you need the initial condition. Without the initial condition, you cannot solve numerically. And why I'm telling that? Because very often I read in the literature saying that on differential equations, saying that in general, ordinary or partial difficult, mostly ordinary, let's consider ordinary, differential equations cannot be solved. The only method which gives you possibility to solve all differential equations is numerical method. For me, it's absolutely wrong statement. For me, the numerical method cannot solve any equation. If you don't have initial condition, you cannot find a solution. Moreover, for analytical methods can give sometimes a general solution with a constant. Numerical solution does not give any constants. So people should be a little bit careful about that kind of general statements. So throughout all analytical methods, consider only analytical or only numerical methods. People are always exaggerating, so you should be a little bit careful about that kind of thing. But anyhow, what group analysis does with invariant solutions? This is one of possibilities to find a solution, an analytic solution. Not all solutions, but some solutions. So here I use initial conditions in order to find one of the solutions. And even if you have partial differential equations, then this equation or system has even more solutions. And there, the difficulty is you cannot, in principle, it's very rare you can break down the general solution of this partial differential equation. One of them is, for example, wave equation, you have one variable, D'Alembert's equation. Then you can write the solution, and there appear instead of arbitrary constants, arbitrary functions. And initial conditions can help you to determine those unknown arbitrary functions. But this is so rare, it's much rarer than in the case of differential equation. Therefore, on the other hand, knowledge of, suppose you have to know the arbitrary solution with arbitrary functions, then in practically all this, except maybe D'Alembert's equation, but maybe some very specific equations, it is helpless. You cannot obtain those functions from initial or boundary or initial conditions. So, in many cases, their knowledge of general solution is helpless. Therefore, what happens? People become interested in particular solutions, and they try to find methods of constructing particular solutions. So, this is a particular solution. Particular means one of solutions or several of solutions. So, idea of invariant solutions is one of these methods of finding some exact solutions, but some, that's why we say particular invariant solution. Not all solutions, but some of exact solutions. They are particular. And it is obtained by requiring that the solution, what you would like to find, is invariant. It means that if you are moving along that curve, the solution, by using the group transformation, the curve does not change. It remains the same. You are just moving along that curve. These are invariant solutions. Now, if you have partial differential equations, solutions are similar, but replacing curves by surfaces or hypersurfaces, multidimensional surfaces, and so on. But now, what is invariant solution on the other hand? It is just some instrument given here, but by the way, it was invented by Sophocles in 1895. And I found it in his paper in 1895, and you can see the reference also in Volker's book, in my books also, it's everywhere. But then people, of course, forget, because this theory was not used for a long time, and it was rediscovered by several people. There was some discussion who was the first. From my point of view, it's not important who was the first. It's good that it was found. But people are people, they are always trying to be the either first. It's like sports. So, invariant solution is a requirement. If you write the condition for the invariance of the solution, you act by the operator x on the solution, obtains 0. It was written already, and I don't repeat it. But as it was explained today again by George Bloom, if you write the invariance condition, it is not always possible to solve this equation for the invariant. You cannot always find invariance for that, or just to solve the condition of the invariance of the solution. So it becomes a differential equation. What is invariant solution? You obtain your. So here I will put many solutions. Okay, here. Now you have the equation f equals to 0. The invariance condition is that you put here some kind of g equals 0. It's a function of x, y, and so on here also. So you add to your original equation some differential equation, which comes from the symmetry group. So it means that it's a differential constraint. You add to your equation additional differential equation and consider together. What it means? It means this equation, these are solutions of your differential equation. Now here is another set of solutions of another equation. And you start investigating the compatibility condition for this equation. So they should have at least one solution. Then it means that the intersection of these two sets should be not empty. And this technique for investigating compatibility conditions was developed at the end of 19th century, or Jean here and so on, but it was, of course, they were not first, but they made the general theory. And nowadays, fortunately, it's very, it's not fortunately, but it was a very difficult problem to investigate compatibility. But fortunately, this terrible work can be done nowadays by computer algebra programs. And that's why they are used for computing symmetries, for computing solutions, invariant solutions or others, or finding symmetries and so on. That's why it's very powerful. Because calculations by hand just impossible to go over. In simple cases you can, but otherwise Very, very difficult. So, and of course, the idea comes to everybody who is just to any person, not only mathematician. But why we start adding this differential constraint using symmetry group? Just add any differential equation, that's it. Write your equations, write another equation, just any equation, but you want arbitrary equation, and investigate their compatibility. So this was also done a long time ago. I think it was done by Euler, because everything was done by Euler. About 200 years ago, at least 200 years ago. And this is called nowadays method of differential constraints. Again, it was rediscovered, but not only rediscovered, but used in very practical way. For example, for solving equation of gas dynamics. And I know the person who was very strong in this, Professor Inyanka. From Moscow, he came then to Novosibirsk, where I was working. And his students, many students were doing this work. Just to take the gas dynamic equations, first, for example, one-dimensional add equations and investigate what kind of differential constraints we can add. One equation, two equations, and so on and so on. And prove theories of consistency. It's very interesting, and after that they can solve some, can find some particular solution. And after the discussion comes, but then why do you need group analysis if you can just add differential constraints instead of adding special constraints? Add any, and you will obtain more general. And of course, you will clear that method of differential constraints gives invariant solution of a particular case of differential constraints. That's it. So they can say that, okay, throw away your method. But each new theory is like that. It comes and says, throw away your theory because I invented more general method. But I think when you come practically, it is both of them are useful. Because some methods are more easy, some less, more powerful. I think using differential constraints, of course, general differential constraints, you can solve